Hey everybody, it's a little noisy right now. I've got my 3D printer and my cutting machine going, still making face shields. But I just wanted to give you a very quick overview of some of the topics, or the topic and then subtopics we're going to be covering this week. Everything we're going to be talking about this week, and even a lot of what goes on next week, has to do with the idea that when we talk about temperature of an object, whether it's got a high temperature or low temperature, what we're really talking about is measuring how much the atoms and molecules inside that thing are moving. So when we think about something that's a solid, right, which we think of lower temperatures, that means that the particles or the molecules in that substance aren't moving very much. They don't have a lot of what's called kinetic energy. They're not moving around. There was a lot of that this week. Okay, so the temperature, when we take the temperature, what we're doing is we're measuring the average amount of energy that those particles have. Some might be a little faster, some might be a little slower, but overall they have a certain average. As that average increases, the particles move more and more, the temperature goes up, and you can start to go from a solid to a liquid by melting. And as you keep increasing that, adding more energy, you're melting the solid to a liquid. The particles get to move more and more. Eventually it's all liquid, the solid is gone, it's melted. Then you can keep increasing the temperature, more and more particles moving around faster and faster and faster. Eventually the particles start flying out of the liquid and become a gas. Okay, and then they can move more and more and more. And if you heat them up enough, you can get to something called plasma, but that's not something that typically happens, under normal conditions here on Earth. So that's the big picture. Okay, that temperature is a measure of how much particles are moving in an object or substance. Okay, the less they're moving, the lower the temperature. The more they're moving, the higher the temperature. And this is where we get to something called absolute zero. Because the concept is, if temperature is a measurement of how much the particles are moving, then when the particles stop, then that's the coldest you can get, because you can't have less motion than stop, right? So if you stop the particle motion, you have reached the coldest possible temperature, which is called absolute zero, which is minus 273 degrees Celsius. It's never been done. Scientists have gotten very, very, very close to that temperature, and we don't think it actually exists anywhere in the universe naturally. But there's a lot of science around super cold, what happens when things get super cold, superconductivity, and things like that. But again, the big picture here is particle motion equals temperature. The next concept is what happens when objects of different temperatures get together. Okay, so what we call heat is just the transfer of energy from an object that's higher temperature to an object that's lower temperature, and it only ever goes in that direction. Something that is cold does not transfer energy or anything like that to something that's hot. Heat goes downhill is one way of saying it. Okay? When you put two objects together that are at different temperatures, the hotter object, which has more energy, will give energy to the colder object and warm it up until they reach what's called equilibrium, thermal equilibrium, which means they are at the same temperature. So this is like what happens if you take a glass of cold water and you put it out on the counter. Well, that cold water is at a lower temperature than the air in the room. That's why it feels cold to you. So the air in the room will start adding more and more of its energy, giving up some of its energy to warm up the water until the water reaches what we call room temperature. So the water and the room are at the same temperature. So heat, okay, is a transfer of energy. So if you pick up a cup of hot coffee, you feel heat. It feels hot to you because the coffee is warmer than your hand, so the coffee is adding energy to your skin cells, heating them up, because the coffee wants to be the same temperature as your hand. So it's going to keep feeding that energy into your hand until either you let go because it's too hot, or the coffee has given up so much of its energy that it has cooled off and now it's at the same temperature as your hand. Equilibrium. In the opposite direction, if you pick up a glass of iced coffee, the coffee is colder than your hand, so your hand is heating up the iced coffee. Okay, so it seems like a weird distinction, but the coffee isn't making your hand cold. Your hand is making the iced coffee warmer. It's doing that by giving away some of its heat, which is why your hand feels colder, because it's getting cooler because it's giving away some of its energy to the iced coffee to try to reach equilibrium. And this is the same thing to think about this kind of on a bigger scale. Right, if you are in a swimming pool, presumably in relatively warm weather, right? When you jump in the pool, it feels cool or even cold, okay? Because the water is colder than your body, and your body immediately starts giving away some of its heat to try to warm up that swimming pool. Okay, now typically, hopefully the water in the pool is warm enough and the air is warm enough that you're not going to lose so much of your energy that you reach hypothermia. But if you stay in cool water long enough, you will start to shiver and your body temperature goes down. So that's why if you were to be crazy enough to dive into water in the Arctic or in the frozen water in the winter, into water where it's cold enough that some of it's frozen, you will very quickly be in trouble because your body is going to try to warm up the ocean, and your body does not have enough energy. Now you can sustain it for a little bit because your body will constantly be generating energy and feeding your body that heat, but that heat is immediately going into the water because your body wants to be at equilibrium with the water. But there's too much water and the temperature is so low that your body can't generate enough energy. Your body will reach equilibrium with the water, but by the time that happens, your body temperature has dropped so much that it shuts down, and that's why you'll die with hypothermia very quickly if the water's cold enough. Okay, so that's this concept of thermodynamics. Temperature is a measure of particle motion. Heat is really just what happens when two objects come together and energy is transferred from one to another. And then the last piece of this is something called kinetics of reactions, reaction rates, and the kinetic molecular theory of reactions. So Legos are always my go-to with stuff like this because there are a couple of things that have to happen in order for a reaction to take place, right? First, the particles, whether molecules or atoms or whatever, or Legos, have to touch, right? If you have two Legos and they're on opposite sides of the room, they're not going to stick together. So first of all, they have to come into contact with one another. That's rule number one. Rule number two is that they have to come into contact in the correct orientation. Okay, so again, think of your Legos. Legos have the dots on one side and they're a recess on the other, or they're flat. If you don't put the Legos together in the right orientation, they're not going to stick because you put the two flat sides together, or you put the two studs together, or you put the two recessed sides together. If they're not stuck together in exactly the right orientation, it won't work. So that's the second thing. The third thing is that they have to come together with enough energy. Okay, there's something called activation energy, which is the minimum amount of energy it takes for two molecules to come into contact with one another in the right orientation, and then for the bonds between the atoms to be broken, because you can't form new bonds without breaking the old ones. And then that will start the reaction, and the reaction will go to completion. But it has to have that minimum amount of energy. So again, thinking of Legos, if you just place a Lego one Lego on top of the other, even though they're touching, even though they might be facing the same way. If you don't press them together with the right amount of energy, they're not going to stick. Okay, so there's a certain minimum amount of force that it takes to get those Legos to snap together, and that's what happens in a reaction too. There's a certain minimum amount of energy that it takes for them to actually have that reaction. Sometimes they come into contact, rule number one, they're in the right orientation, rule number two, but they're just not going fast enough or with enough energy to kind of smash apart and form new bonds. So they just bounce off and they go their separate ways. So one of the things that's going to be in this this week is the fact that there are different ways that you can improve the odds of these reactions happening. One is you can increase the temperature. Typically, that will increase the rate of a reaction. Why? Well, remember, what's temperature? Temperature is a measure of how fast the particles are moving. So the faster the particles are moving, first of all, the more often they're going to bump into each other because they're running around really fast. And when they do run into each other, they're going to have more energy. So if you heat them up, they bump into each other more, they bump into each other with more energy, so more of them are going to get over that threshold of the minimum activation energy. You can also increase the surface area. So if you take like a solid of something, a solid piles of combustible material, if you put a flame to it, it will probably eventually burn, but it won't burn very quickly. If you take that same material and you grind it up into a powder and then put that powder into the air, so you have all these little teeny tiny specks of combustible material with a massive amount of surface area, because every little ball has its own surface area, boom, that's how you can get an explosion. Okay, because now you have exposed all those particles, so the number of collisions between the particles of combustible material and the air and the ignition that it needs to combust goes up. So the more collisions you can get, the better. If you constantly agitate or stir something, you can increase the reaction because, again, you're increasing the number of collisions, you're giving it a little bit of energy, and you get more reaction faster. And then finally, one little trick that scientists use and industrialists use all the time is they use something called a catalyst. So a catalyst is something that doesn't actually react, but it kind of gets in there, and what it does is it lowers the activation energy required. So it allows the reaction to happen at a lower threshold than it normally would. That allows more of those collisions to take place. More of them take place with enough energy because the bar is lower. More of them get over that bar. So the reaction goes faster. And then the catalyst, the great thing about catalysts is that they don't get used up, so you can reuse it later. Okay, so catalysts are really important in industry because A, they make the reactions go faster. They make them, or not faster, they make them go with less energy. So you don't have to heat it up as much, which takes energy and costs money. And they can be reused. So those are some of the things that you're going to be talking about this week. And then there's the last thing called equilibrium. Equilibrium, I talked a little bit about with thermal equilibrium, right? Two things get to the same temperature. Well, equilibrium in a reaction, some reactions can go in both directions. All right, so you have A and B becoming AB as a compound, and some of that AB breaks up and produces A and B again. So the reaction goes in both directions. Well, once the concentration of the starting material and the concentration of the ending material get to the same point, get to the same, not the same level, but a fixed level, the reaction is still going on back and forth, back and forth, back and forth, but it's kind of like a treadmill. Just as quickly as the forward reaction is happening and A and B are combining to form AB, at the exact same rate, AB is breaking up to form A and B again, all over the reaction. So the result is that the amounts don't change, because every A and B that combines, an AB breaks up. So again, like being on a treadmill, you're going forward, but the treadmill's going backward, and if you're doing it right, you're not going anywhere. But it doesn't mean you're not working. It doesn't mean nothing's happening. It just means that the two directions are canceling each other out. So that's equilibrium in a nutshell. So this week it's just watching the videos and answering the questions. And then next week, the next week plus a couple of days, We'll be wrapping up with more stuff with temperature and gases specifically, and then just sort of some wrap-up material, and then there'll be a few days at the end for any makeup work that you might need to do. So anyway, that's a quick overview of this week.